Hello everyone, my name is Yeqi Gao from Tsinghua University. It's indeed a pleasure to be present here today to share insights into our latest research titled Solving Tensor Low-Rank Approximation. I collaborate this work with Yichuan Deng from University of Washington and Zhao from Adobe Research. Throughout this presentation, I will provide a comprehensive overview of our contributions and underlying ideas from the basis of our work. I encourage of all those who are interested in our work to contact with us. All contact information, including email addresses, is conventionally provided at the bottom of the first page of the slides for your reference. Now let us start our presentation. In our exploration of this research landscape, we dive deep into the development and current state of large language models, emphasizing the pivotal role of theoretical breakthroughs to enrich our understanding. Allow me to outline our main contributions. Firstly, we introduce the concept of control tensor rank. This innovative idea holds the promise to illuminate previously uncharted dimensions of large language models, potentially revolutionizing our approach to comprehending their intricacies. Furthermore, we present a circle tensor low-rank approximation algorithm designed to efficiently address the low-rank approximation problem. As we progress in our presentation, we will focus on three main aspects. Why did we propose the concept of circle tensor rank? What insights our challenge led us to this novel exploration? What constitutes the low-rank approximation, and how does our proposed algorithm efficiently tackle this problem within the context of circle tensor rank? How do we establish the correctness of our algorithm, and what is the time complexity associated with the implementation? In recent years, we have witnessed the exponential growth of large language models, marking a revolutionary era in fields such as natural language processing, AI-driven content creation, and language translation. However, despite their widespread application and continuous advancement, there exists a notable gap in our understanding, a gap created by the absence of comprehensive theoretical frameworks that can provide a deeper insight into mechanics underlying these models. This disparity underscores the crucial need for theoretical studies and research to bridge the gap and offer explanation for empirical success of large language models. Our research places a focus less on addressing this need. We are committed to contributing to the theoretical understanding of large language models, with a specific emphasis on exploring the concepts of tensor circle rank. As we progress through our presentation, we will unveil the motivation behind our research, the challenges we seek to address, and the potential impact of our contributions on the broader landscape of theoretical research in the domain of large language models. Let's now continue talking about the motivation behind our research, a motivation grounded in recent advances in understanding of how transformer operates within the realm of natural language processing. In a noteworthy publication by Zhao, a critical question was posed: is transformer capable of true parsing while adapting mask word prediction? This work dives into the intricacies of transformer models and their capabilities in context of language processing. Of particular interest to us is exploration of probabilities, content-free grammar, and its parsing algorithms. The central theme revolves around understanding the transformer's ability to engage in genuine parsing activities, especially in scenarios involving masked word prediction. Our journal from probabilities content-free grammar (PCFG) to concept of circle tensor rank represents a significant evolution in our exploration of language models. PCFG, a fundamental model in natural language processing, serves as our starting point. It's a crucial tool for understanding the probabilities structured inherent in languages. In the context of large language models, PCFG takes a pivotal role in unveiling the parsing behavior of these advanced models. However, when we encounter a computational challenge, particularly in efficient computing probabilities for grammar parsing, this challenge arises due to the involvement of intricate tensor operations. To address this, we introduce the novel concept of circle tensor rank. This introduction is motivated by intriguing similarity between the circle index and the magical probability. Let's dive into the marginal probability of PCFG. Our focus is on the computation of the improbability. This involves a process we consider three variables ij and a. Here's how it works. For each combination of other two variables, let's call them b and c, and for each variable k that's ranged between I and 1 less than j, we perform a statistical calculation. We multiply the improbabilities of ik and b and k plus 1 j c together. Then this product is further multiplied by probability of a transmission to both b and c. This approach allows us to transform these variables into what we term as circle indices and tensor indices, derived from the improbability. By doing so, we can draw meaningful insights from the computation of the improbability. This method is fundamental in defining the circle rank of a tensor, a concept crucial for our research in low-rank approximation. Our aim is to simplify and streamline complex calculations, making them more accessible and understandable. Now we will introduce our definition of tensor circle rank. A cornerstone of our study, we began with three matrices named U, V, and W, each residing in the real number space sets the n by k squared. A tensor which we will refer to as A is said to have a circle rank of k if it meets certain criteria. Let's break this down further. The matrices U, V, and W are actually tensors with dimensions n by k, containing real-valued entries. The circle rank is defined based on a specific condition that this matrix must satisfy. For each index I, j, and l of tensor A, its value is sum over three variables, which we label as A, B, and C, each ranging from 1 to k. The value at A for indices I, j, and l is obtained by summing up the products of U at index I, or plus k times b minus 1, v at jb plus k times c minus 1, and w at lc plus k times a minus 1. Optionally, we can express this in another way. The value at A for ij and l is the sum of products u at iab, v at jbc, w at lca. This dimension circle rank forms the backbone of our approach to understanding manipulated tensor in low-rank approximation context. Let us move on our main result, the tensor low-rank approximation algorithm. This theorem addresses a third-order tensors, which are a form of multidimensional arrays residing in a real-world space set n by n by n. The theorem says that there exists an algorithm effective for any value of k that is greater than or equal to 1, and any epsilon between 0 and 1. This algorithm operates in a specific time frame, which is the sum of the non-zero elements of A plus n times an polynomial function of k and the inverse of epsilon plus exponential of another polynomial function of k divided by epsilon. Now, what does the algorithm do? It produces three tensors u, v, and w, each with dimensions n by k. These tensors meet a critical condition. When sum the products of u, v, and w for each combination of indices from 1 to k, then the subtract tensor A from this sum, the frobenius of this result is less than or equal to 1 plus epsilon times of the minimum frobenius norm of the difference between tensor A and another tensor AK, which has a circle rank K. In simple terms, this theorem is a breakthrough in making the computation of tensor low-rank approximation much more efficient. It provides a practical and precise method to handle complex hand-dimension data, enhancing both efficiency and accuracy in our computations. In this section of our presentation, we are going to provide an overview of the core techniques and that underpin our algorithm. Understanding these techniques is crucial for grasping how we approach the problem of tensor low-rank approximation. Our analysis is divided into three key parts: rotated sketch sets. Here we will explore a series of sets that involves rotating and sketching the data. This process is pivotal in simplifying and restructuring the problem, making it more manageable. We focus on transforming the data into a format that's conducive to our specific data of analysis. The second one is input sparsity reduction. This part of discussion revolves around reducing the sparsity of the input data. Sparsity refers to the amount of zero or near zero data in the matrix. By reducing this sparsity, we make the matrix more dense. The third one is solving small problem where polynomial system solver. Finally, we address methods for taking smaller, more specific problems within our larger data sets. This involves utilizing a polynomial system solver, a tool that helps in finding solutions to polynomial equations. By breaking down our larger problem into small components, we can apply these solvers more efficiently. Now we will introduce our first step of technique. We start by concentrating on a regression problem. The objective here is to find a matrix U within a specific real-world space of dimensions n by k squared, which minimizes the difference between tensor A1 and product U with another matrix Z1. The difference is measured using the frobenius norm, a method to calculate the magnitude of a matrix. To efficiently solve this regression problem, we use an optimized version of U, which we denote as height U. This height U is a matrix that minimizes the difference between the products of UZ1 S1 and A1 S1 again, minus use the frobenius norm. We aim to achieve an approximation where frobenius norm of difference between A1 and the product of height U with Z1 is less than or equal to 1 plus epsilon times the minimum of frobenius of difference between A1 and the product of any matrix U with Z1. Now in the final, we can establish the existence of a matrix that satisfies our bulk conditions by choosing height U as a product of A1 S1 and the inverse of Z1 S1. Here, height U falls within the column span of A1 S1 and can be represented as A1 S1 multiplied by some matrix S1. In the stage of our presentation, we build upon the fundamental laid in the first with rotate sketch step 2. This step is crucial in the development of our tensor approximation algorithms. Creation of a rank K tensor based on the outcomes of step 1. We now focus on constructing a rank K tensor, which we denote as B. This B is denoted as the sum of products of elements from our optimized matrix height U and two other matrices U V star and W star across all possible combinations of indices from 1 to k. Each element in B is calculated sum of tensor products, a mathematical operation combining this matrix. Redefining Z2 with respect to height U, we then redefine another matrix Z2 in relation to height U Essentially, each row of Z2 is vector formed by summing the tensor products of height u and width star for specific combination of indices. The second step, we need to solve a new regression problem. The goal to minimize the difference measured by the Frobenius norm between the products of a matrix V with Z2 and another tensor A2. By retensoring the products of an optimized height V with Z2, we obtained our matrix B. The Frobenius norm of the difference between B and A is then ensured to be less than or equal to 1 plus epsilon squared times the Frobenius norm of the difference between another tensor AK and A. Continuing with our technique deep dive, we now proceed to rotate and sketch step 3, which mirrors the approach of the previous step while introducing new elements. Similar to the previous step, we consider matrix Z3 within a specific real number space. The rows of Z3 are vectors, which are the tensor products of specific elements from A1S1 and A2S2. Another regression problem. We encounter a new regression problem here, focusing on minimizing the difference measured by the Frobenius norm between the products of matrix W within Z3 and another tensor A3. And we find the optimal matrix B. Our objective is to find a matrix such that the Frobenius norm of difference between B and A is less than or equal to 1 plus epsilon squared times the Frobenius norm of the difference between another tensor AK and A. This quantifies as 1 plus O of epsilon times of the Frobenius norm of the difference between AK and A. With this step, we further solidify the basis of an optimal decomposition of matrix A. We are now set to shift our focus toward optimizing the efficiency of our algorithm, leveraging the insights and methods developed in these steps. In this section of our presentation, we focus on two critical aspects of our algorithm: input sparsity reduction, solving small problem very polynomial system solver. Input sparsity reduction to meet our running time guarantee, which is a function of a polynomial of k over epsilon, plus number of non-zero elements in A. We modified the matrices S1 and S2. We achieve this by using a sparse count sketch matrix in combination with a Gaussian matrix. This step is vital for efficiently managing our data and ensuring the algorithm run within the desired time frame. Solving small problems via polynomial system solvers, we begin by expressing matrix UVW as products of A1 S1, A2 S2, and A3 S3 respectively. Our objective is to minimize a degree 6 polynomial to achieve a close approximation. This is done by carefully choosing indeterminate variables in polynomial function. We utilize polynomial solvers to ensure that the error is bounded and manageable within the polynomial time of n. The goal is to find solutions that are at least 1 plus a small factor of epsilon, close to the optimal. Throughout these sophisticated techniques, we enhance the efficiency of our algorithm, especially in handling sparse inputs and break down the complex problem in a small, manageable parts. As we conclude, let's recap the significant contributions and the implications of our work. Introductions of new tensor rank, circle rank. We have introduced the innovative concept in the field of tensor analysis, the circle rank. This new tensor rank is the cornerstone of our low-rank approximation algorithm for third-order tensors. Emphasis on theoretical fundamentals in large language models. Our work underscores the importance of having a solid theoretical foundations, particularly in repeatedly evolving domain large language models. This is crucial for keeping pace with the technological advancement in this field. The ultimate goal of our research is to provide a deeper insight into the theoretical aspects of natural language processing and related areas. We believe that our contributions will significantly advance the theoretical understanding and practical applications of large language models, driving forward the frontiers of knowledge in this exciting domain. Thank you.